Hey, Fraser. Okay. All right. So the last chunk of notes for this section. The math on this is very, very easy. All right. There's one simple equation. The main thing is just going to be then applying it. Okay. So here we go. Last year / a couple chapters ago, we learned that an object that is moving linearly has momentum. Yes. This little apple has momentum. Okay, to calculate the momentum, remember, it's just a product of mass times velocity. Okay, and remember, mass is a measure of inertia. So we could say it's inertia times linear velocity, right? Okay, so this whole last couple chapters, we've been talking about kind of the angular counterparts for all the linear stuff we've learned. So now we need to learn about angular momentum. This is something we did not learn about last year. This is brand new for all of you, all right? So, and the equation is exactly what you think it is. All right, so the symbol for angular momentum is capital letter L. Okay. Symbol for angular momentum is a capital letter L, and the equation is exactly what you think it is. It's instead of inertia times velocity, it's rotational inertia times angular velocity. Cool? Yep. All right. Now, when you define your angular momentum, you have to define your origin. Okay? So what I mean by that is, so the apple had linear momentum, right? If I take this wheel and spin it, I can talk about its angular momentum about this point, right? Yeah. Okay? If I rotate it this way, that's a different amount of rotational inertia than this, right? Because it's got a different rotational inertia, right? Okay, that will become particularly important in the last example we're going to do today, which is not in your packet, but you'll see. All right, so in the same way that the direction of linear momentum is in the same direction as the velocity, right? Momentum is in the same direction as the velocity. Your angular momentum is in the same direction as your angular velocity. Which is fairly intuitive, right? I mean, if the wheel is spinning clockwise, then the momentum is clockwise, right? Cool? Cool. All right, so that is that. All right. So, real quick, I put this little chart together, you guys, that just kind of summarizes all of this angular stuff that we've done this chapter. So, there's a lot of letters here, so just make sure you're good with this. And the big thing that I want to point out here is all of the linear equations, I think you guys know from last year, the angular equations are exactly what you'd think they would be, right? Mass is replaced by rotational inertia, velocity is replaced with angular velocity, force is replaced with torque. Cool? Yeah. All right. Does anybody want me to say anything more about any of this? Oh, I guess let me say this. So, when we did momentum, one of the things we learned was that change in momentum, the only way you're going to change momentum is if you change velocity, right? Okay? And that change in velocity is produced by a net force acting on a thing for some amount of time, right? Everybody cool with that? Does that ring a bell? Yeah. All right, so, I guess I'm glad I stopped here. So this is the angular counterpart for that same equation. Okay? Our change in angular momentum. Well, the only way you're going to change angular momentum is if you change angular velocity, right? And the only way that's going to happen is if you have a net torque acting on the thing for some amount of time. Cool? All right. Remember, change in momentum is what. So this works if your net force / net torque is constant. If not, then you got to do integrals, right? So remember, impulse change in momentum is the integral of net force with respect to time. Similarly, your change in angular momentum is equal to the integral of net torque with respect to time. Cool? Alrighty then. And then you can go the other way and differentiate. Remember, we said that Newton defined net force as the rate at which momentum changes. Similarly, net torque is the rate at which angular momentum changes. Cool? Newton's second law, net force over mass. Newton's second law, net torque over I. All right. Cool? Totally thought you were eating my apple. Are you okay? Did you just lose a tooth? I see. They should make jawbreakers that are shaped exactly like apples.
Oh, that's not
All right. Okay. All right. So when we did momentum, one of the big concept we learned about was the idea of conservation of momentum. Right? Anytime two objects interact and there are no external forces, your total momentum is the same before the interaction as after. Clear? All right, so it turns out that the same is true with angular momentum. All right, as long as there are no external torques, then your angular momentum remains constant. Okay, so in a minute, let me do a numeric example. Let me first of all just show you a visual example. All right, so where did I put my bricks? Oh, right here. Can I get? Oh shoot. You guys might want to scoot your desks back a scope so you don't get smacked in the face with a brick.
Oh, that's great.
Yeah, I know, right? Okay, so,
Can I move forward and not have to go to school for
all right, so I've got some bricks here. I'm going to spin around. You ready? Here we go. Okay, so right now, because my mass is far from my pivot point, I have a large amount of rotational inertia, right?
Bring the bricks in.
Okay? Everybody agree? The mass is far from my pivot point, large rotational inertia. If I pull my arms in, what am I doing to my rotational inertia? Decreasing it. Ah! All right? Now I'm super dizzy and I'm going to pass out. All right? So in that example, so that's usually referred to as the figure skater example, right? You've all seen, like on the Olympics, right? Figure skaters spinning, they pull their arms in and spin really fast. Yes? Okay? So, now, think about this. When I pull the bricks in, am I producing torque? No, because my lever arm is straight out the length of my arms, right? And all of my force is inwards along the radius, right? So there's no perpendicular component of the force. Follow? So I'm not producing torque when I pull my arms in, right? Okay? So the idea is, with my arms out, my angular momentum is a large rotational inertia times a small angular velocity, right? Then I pull my arms in, which has the effect of decreasing the rotational inertia and increasing my angular velocity. But it's still the same amount of angular momentum. Does that make sense? All right. Next time you go to farms, watch them spin their pizza dough. What's the point of spinning the pizza dough? Stretches out, right? So what happens to the rotational inertia? They spin it up into the air, it spreads out.
And it slows down.
The rotational inertia increases, right? Because your mass is farther out. So what should the dough do as it spins? Slow down, right? Cool? All right. Another example that I've seen. So global warming. People are worried about the polar ice caps melting. So right now, all of that mass is at the North and South Pole, right? If it melts, where's it going to go? It's going to disperse farther out. What would that do to the Earth's rotation?
Make us go.
Would it make us go faster or slower? Slower, right? Because you're taking mass from the poles and moving it. Some of it's going to spread out. Some of it's going to spread out to the equators, right? Like, so here's the Earth. Here's all your ice, right? All right, then the ice melts. Oh, that was supposed to be black. So here's the ice now. Right? It's more spread out instead of all being concentrated here. Right? Okay, questions on that? Yes?
sea level higher at the equator?
Do you mean like radius-wise?
Like, say you had like...
I don't know the answer to that, but I think I know what you're asking, and my knee-jerk reaction is yes. We got a lot to get through. Let me look into that, and can we talk about it more another day? All right. Okay. And in fact, when we do gravitation, ask me that question again. I'll find an answer by then. All right. Everybody good? Okay. Now, so let's do a numeric example. All right? And you should have this in your notes. So on a playground, there's a small disc-shaped merry-go-round of radius 1.2 meters and a mass of 160 kilograms. Sally, who has a mass of 40 kilograms, oh, I guess we don't need to do the second example. This hits the same thing as that second example does.
Nice.
Good, so we only have one example we got to get through. All right, so let's make two drawings. Let's do a before drawing. All right, so here's our merry-go-round. Merry-go-round. So what do we know about the merry-go-round? It's got a radius of 1.2 meters. It's got a mass of 160 kilograms. All right, and then we've also got Sally, who has a mass of 40 kilograms. It says she runs at a speed of 3 meters a second along a path that is tangent to the rim of the merry-go-round. So here comes Sally like this. Cool? All right, so everybody good so far with what's going on? So she's going to run. This is like a top view. So she's going to run along and jump onto the merry-go-round. If it was initially at rest, she would be, pushing it and make it spin, So it's, here's the merry-go-round, here's Sally, jump. Follow? All right? But to complicate things, the merry-go-round is spinning at the beginning. All right, so it says the merry-go-round was initially spinning towards Sally with a period of 8 seconds. Ugh. Why did I write this like this? So I'm going to write T for period initially is 8 seconds. It says it's spinning towards her, so I'm going to draw. Make sense? Why would she? Because somebody's chasing her, Jacob.
Wouldn't she like rub them?
All right. She doesn't have time to think about it. She's just reacting. So there's a boy with cooties. All right, let's see. So we're gonna no friction or anything. Okay. So part A says find the initial angular momentum of the merry-go-round about its axis of rotation. Okay. So I guess before I do that, are there any questions on just all this given info here?
I have a question.
Yeah, shoot.
Would it make it easier to just change the period into an angular?
Yeah, that's exactly what we got to do. It is exactly what we got to do. Okay, so if you didn't just hear him, Adam just said, would it be easier to convert the period to, would you say, angular velocity? It's exactly what we need to do. Okay, so what I am hearing you say is this. We need to know the initial angular velocity of the merry-go-round, right? So how do I use that 8 seconds to find the initial angular velocity? Sure, we got time.
Switch it into frequency and then times it by 2 pi.
Okay. And so how do you switch it into frequency?
Just taking a
Reciprocal, right? Okay. It's this. It's going to go through 2 pi radians angularly, right? That's one rotation in 8 seconds, right? Follow? All right. So that gives us a number somewhere. I think I actually have this worked out. No. All right. What's it give you? 741?
I got 785.
785? Okay. Sorry. Okay, so that's that. What else do I need to know in order to find that angular momentum? we need to know our I, right? Okay? The problem tells us it's disk-shaped. So our I for a disk is 1/2 mr squared. So that's 1/2. The mass was 160. The radius is 1.2. Don't forget to square it. So you get 1.44 times 80 is 115.2 kilogram meters squared. Everybody good? All right. So L for the merry-go-round initially is going to be I omega, which is 115.2 kilogram meters squared, times 0.785 radians per second, which gives you 90.5, is that right? All right, so here, this is an important thing, you guys. The units for angular momentum are not the same as the units for regular momentum. Okay? Regular momentum would be kilograms times meters per second, right? This gives us kilograms times meters squared per second. All right, and the radians magically disappear. We'll leave it at that.
Show us how the radians disappear.
It's really not important. It comes out with this I, the way this rotational inertia is calculated. When you multiply by R, one of those R's is a meters per radian. All right. Okay, cool or no?
Cool.
All right, that's why we have wizard heads. All right, because you can make radians disappear. All right, questions on part A? Yep. All right, everybody good? No? See a couple people scribbling. I will wait. Got it? Yep. Everybody else set? Okay, now, part B. Part B wants us to know the angular momentum of Sally initially. So this is weird, because Sally is running linearly, right? So how does she have angular momentum? All right, so if you go back to the drawing, remember I said angular momentum only makes sense with respect to a pivot point? I don't know if I said pivot point, but an axis of rotation or whatever I said. Yeah. So our axis of rotation here is the center of the merry-go-round, right? So do you agree that at this instant, at the instant she jumps onto the merry-go-round, she's got tangential velocity about that pivot point, that axis of rotation? So we can find her corresponding angular velocity, right? Follow? All right, so it turns out there's a little shortcut you can use to find the angular momentum of a point particle. I'll be honest with you, I can never remember what the shortcut is, so I always just figure it out, okay? So we can, if you want, we can figure it out real quick though. So look, it's I times omega, right? So what's I for a point particle, you guys? Mr squared, right? So this is Mr squared times, let's see, we don't know what omega is, we know what V is, but what's the connection? Just V over R. Oh, so there it is. Our R's cancel, so it's just MVR. Aha! Does that make sense, you guys? Now, if you wanted to, you could do it in two steps. You could find her rotational inertia about the center of the merry-go-round, find her angular velocity, and multiply. Okay, but I think this is a little bit easier.
So what is this again?
This is getting us Sally's initial angular velocity, or initial angular momentum. Cool? Any questions before I plug my numbers in? All right, so let's see. Her mass was what, 40 kilograms? Her velocity was 3 meters a second. The radius of the merry-go-round is at 1.2 meters, is that right? Yep. So 1.2 times 3 is 4.8 times 480 is 196. Is that right? I don't think so either.
It should be 4 times, so it's like 12, 12, something like that.
Yeah, I'm sorry. How about if I don't do stupid math in my head? Is it 144?
Yeah.
Thank you. Sorry. I was all excited. I almost said how smart I was, but I'm glad I didn't, because I was wrong. All right. All right. Everybody cool with this? All right. I have overlooked a very, very, very important thing. Oh, there it is. I was going to pick on you and you said it anyway. Yeah, say it again, Jacob.
Oh, one of them's negative.
One of them is negative. Why? Because the merry-go-round is spinning towards her. So according to my drawing, the merry-go-round is going clockwise, but her angular motion is counterclockwise, right? Follow? So we need to go back up here and tack on a negative sign. All right, so now I know the angular momentum of the merry-go-round before she jumps on. I know the angular momentum of Sally right before she jumps on. What should I probably do? Add them. Find the total momentum of the system, right? So what is that what question C asks? No.
So is clockwise traditionally negative then?
Correct.
Really?
Yeah. And it's the same thing you do in math class, right?
Oh yeah.
Like if you go this way, that's positive, and this way is negative when you're measuring angles. Yeah, I know, that's annoying. Okay. So this means that our total angular momentum before the interaction between Sally and the merry-go-round is negative, what was it, 90 point something? 90.5? 90.5 plus 144 is going to give us, what, 54.5? 53.5? Man. Kilogram meters squared per second. All right, are we good? All right. So now what has happened is this. So we started out with our merry-go-round spinning. Sally runs and jumps onto it, right? And then we don't know what's going to happen. Oh, well, actually, I guess we do. Our total angular momentum is positive, right? So it's got to be spinning now in a positive direction, right? Follows? So let's see. This one's the merry-go-round. This one's Sally. So Sally succeeds in pushing it back the way she was running. Follow? All right. So question C says find Sally's speed after she has jumped onto the merry-go-round. So after So we know that our total angular momentum final is equal to the angular momentum of the merry-go-round final plus the angular momentum of Sally final, and we even know that that's 53.5, right? All right. There is something very, 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 very important that we need to recognize in this problem.
I changes.
Well, Sally's still sort of at the outside edge, isn't she? So she's still got the same mass, the same radius. The merry-go-round's mass and radius haven't changed. What did Sally do?
She increased the mass of the system as well.
Well, that's going to be accounted for in her rotational inertia.
Oh yeah.
She applied a force to the merry-go-round. Let me say this. I'm trying to figure out how I can steer you guys in the right direction without just telling you what I want you to realize. So when we did collisions, we learned that there were 3 types of collisions, right? Elastic, inelastic, and perfectly inelastic. Patrick, you just said third one, perfectly inelastic. What are you talking about? Doesn't she stick to the merry-go-round? Right? So what does that mean about their... Talk to me about linear or angular velocity. Something's true. What are the same?
Angular velocity.
Same angular velocities, right? She's on the outside edge of the merry-go-round, rotating at the same angular velocity as the merry-go-round itself, right? Follow?
Yeah.
Yes.
So would it work to do 53.5 equals IW?
Exactly. So now we got to go IW. Exactly. So we want I of the merry-go-round times omega, final, plus I of Sally times omega, final, where omegas are the same, right? Does that make sense? All right, so we can do this. Let's see. So I for the merry-go-round, we had already found that, didn't we? I for the merry-go-round is 115.2. Do you guys care if I leave the units off? Is that going to mess anybody up?
No.
Okay. Times omega f plus I for Sally. How do I find Sally's rotational inertia? mr squared, right? So her mass is 40, and her radius is 1.2. Don't forget to square it. Times omega f. Holy moly, we just did it, right? We're pretty much done now, right? All right, so let's see. So we're going to get 53.5 equals, let's see, 40. That's the one that's 192, right? Am I doing it right yet? 144 times 40, or 1.44 times 40? No, what am I doing? Failing at life is what I'm doing. 115.2 omega f plus 57.6 omega f. So this gives you 0. We'll just call it 31 radians per second. So let me pause there for a minute. I did a bunch of algebra. Did I lose anybody? Either in, well, I guess let's do this first. Is everybody good up to here?
That rotational inertia for Sally is mr squared, right?
Yep.
Okay, cool.
Yep. Rotational inertia for Sally is just mr squared. So mr squared. Everybody follow? All right, and then it's just algebra. Are we good?
Yep.
All right, so what was question C asking us? The speed after she's jumped on the merry-go-round. So how do I find her speed?
Multiply by the ratio.
Yeah, just do a jumper. V equals omega r, right? 0.31 radians per second times her radius, which is 1.2 meters. That gives you, what is it? 0.372. Thank you. Good? In the same direction she was already running in, right? Any questions? All right, one last question. Part D, find Sally's speed after she crawls halfway to the center. All right, so first of all, if she crawls towards the center, is she applying a torque?
No.
No, because her force is parallel to the lever arm, right? Follow? Okay? So really, part D is exactly the same thing we just did with one tiny little exception. Change which radius? This 1.2 becomes half of that, right? So 0.6. And then you just recalculate it again. Do you think you will get a bigger or smaller angular velocity? Bigger. Why? It's just like pulling your arms in, right? Literally the exact same thing, right? You're moving your mass closer to the center, less inertia, faster angular velocity. Now, does that mean she'll have a faster linear velocity? I don't know. We'd have to figure it out. I don't think so because of the squared here. So I think it actually does. Let's see. That's going to be the. I don't remember. Do you guys? Well, here. Let me see. All right. So how did we do? Is that what we got? Oh, just different signs, but same idea. Same idea. Same idea. And okay. So it does turn out to be slower. So the final answer turns out to be 0.25 meters a second. So even though it sped up angularly, because she's closer to the center, she still has less linear speed. It's cool? Questions? Yes? We're not going to be in here because of the washout.
Is it all out?
It's 17.
Yeah, I mean, it's not supposed to be, but it will be, just knowing how things work. Yeah. All right, questions on any of this, you guys? All right, one real quick thing. There are a couple questions on the homework that have problems like this, where, you know, a thing will crawl in towards the center and your angular momentum is conserved. Some of the questions ask you to calculate the rotational kinetic energy before and the rotational kinetic energy after. Okay? And sometimes your rotational kinetic energy increases, sometimes it decreases. So as you're doing those problems, think a little bit about why that would happen. Like, what does this have to do with work, etc.? Okay? So anyway, we'll talk about that one after you guys have had a chance to try them a little bit. Okay? Questions? All right, I'm going to give you guys the last 15 minutes to work. Will you use it to work?
Yes.
Excelente.
So, Mr. Hacker,
Yes.
even if you don't participate,